C++ language. Several libraries already existed to read and write FITS files in C++. Yet, none of them provided the type safety we'd expected. Therefore, we have internally developed LFITS, which is both safer and easier to use. It is also as fast as CFITS.io, not to say faster in some circumstances. As an example, here is how to create a single image FITS file with one keyword record using CFITS.io. Now, using CCFITS, and finally LFITS. More compact code with less parameters means less development errors. On performance side, LFITS is equivalent to CFITS.io. Yet, internal optimizations for tables dramatically reduce runtimes as compared to the classical usage of CFITS.io. Come join us at the poster sessions and have a look at the library on GitHub.
My name is David Keiderling. I'm from the Max Planck Institute for Solar System Research in Göttingen. We are a main contributor to the science ground segment of the European Planet Detection Mission Plato. I want to bring to your attention my poster with the title Distributed Development of the Level 1 Data Processing for the Science Ground segment of the ESA Plato mission. In this poster, I introduce some key aspects of our development and how we create science-ready data products for the Plato Science Ground segment. I would like to invite you to have a look at the poster, discuss it with me, and exchange some experience. See you at the posters. Thank you very much.
My name is Marcos López Caniego. I'm an astronomer working at the ESA Science Data Center. I'm going to tell you about the James Webb area of ESA Data Labs. ESA Data Labs is a science exploitation platform sitting on top of the astronomy archives at ESAC. And when it becomes publicly available in a few months' time, users of Webb will have a place to come and explore and analyze data. Our platform is based on Docker containers and Jupyter Lab, but it also works with Jupyter Notebooks. So the users of Webb, they will also have access to PySky, our Jupyter Lab widget for ESA Sky, and that includes the James Webb planning tool to help prepare future observations. And it also includes several example notebooks to show users how to explore our archive, and also how to analyze data using the STSCI provided data analysis notebooks. So we hope you like the poster, and please do not hesitate contacting us. Thank you.
Hi, my name is John Swindling. I work at Astron, the Netherlands Institute for Radio Astronomy, and I'm the coordinator of the ESCAPE project's Work Package 5. ESCAPE is a major European project putting together solutions for data-intensive astronomy and particle physics. We're developing data lakes for dealing with massive data volumes, cutting-edge scientific software repositories, deep integration with the virtual observatory, and gateways to citizen science projects. You can learn more about all of these across this conference. Here, though, I'd like to draw your attention to ESAP, the ESCAPE platform. ESAP is our effort to put together not a single science platform, but a toolkit that you can use to build and customize a science platform for your specific project or application. I hope you'll check out our poster, and I hope you'll find ESAP useful in your own work. You can see my email address at the side of the screen, and I'd love to hear from you with any comments and questions, and I hope you'll enjoy the rest of the conference. Goodbye.
Hi, my name is Anastasia Alexa, and my poster is on the struggles to find a good electronic document management system for the DKIST project. The DKIST project does have a document management system, but we wanted to find a different system with lower cost, less complex, more modern, and with easier workflows for over 1 million documents and 500,000 different folders. We tried over 20 different products that were either too expensive, difficult to manage, or were not recommended. And we came up with Box and Box Relay. It was by far the best product that we had tested. It's similar to Dropbox. It has native workflows. It has native approvals and native signatures. It's modern. It's cloud-based. It's FedRAN compliant. That means it has high security. You can put your 99 and ITAR data in Box. It requires minimal administration. It has workflow histories. We found it by far to be the best product out there. And we hope that you find this investigation useful to possibly replace your electronic document management system, which I know a lot of you have been struggling with yourselves. Thank you very much.
I'd like to talk how to use computing and data science to accelerate knowledge discovery in astronomy, where I focus on automated spectroscopic analysis of X-ray data The methods described here are also valuable for many applications that have a large data set. Genetic algorithm is a class of heuristic method inspired by the theory of evolution, using selection, crossover, mutation to find optimized solution. We applied the GI method to a starburst galaxy NGC 253. Manual fitting and automated GI fitting match quite well in a wide range when the same physics models are selected. However, our GI code only requires a few minutes running without human intervention, making it itself a high-performance method to leverage the information collected through instruments. Thank you.
In order to address astronomical data in its big scale and variety, we propose a web application that helps researchers to explore datasets with the help of machine learning. UltraPing performs dimensionality reduction by training a self-organizing coordinate map, SOM in short, and allows you to organize, inspect, and interact with these maps. Visit a SOM and you'll see a topology of generated images, prototypes representing the most common shapes in your dataset. You can select individual prototypes or multiple at once. Change between multiple views, like one that shows you an overview among the given labels. The heat map view informs you about how many data points from your set match best to a prototype. For each prototype, you can request the best matching data points. The data points themselves can be inspected in an individual page with a LED in light. Key feature of UltraPing is the abstract design pattern of its function set, which is continuously growing with the goal to create the ultimate explorer's toolbox for you data jungle adventurers.
Hello, we are going to introduce you to our project PyCF3. PyCF3 is a Python library that integrates the web service of CosmicFlow's 3-distance velocity calculator with the Python scientific stack. It pursues two main objectives: to accelerate local computation times, and to not overload the server with repeated calculations. For example, if we instantiate a connection to the CF3 calculator and perform the same distance calculation twice, the second call accesses a local cache, accelerating the process to approximately 2 or 3 microseconds. The results has all the attributes that are available in the web version, and they can be accessed as a NumPy array, as well as the raw result in JSON format. Finally, the project follows a strict quality standard and has detailed documentation. If you have any questions, please do not hesitate to contact us or visit the project website. Thank you.
So hello everyone, my name is Eku Biorishek and I'm from University of Geneva, and I would like to invite you to check our poster on reconstruction of data from LST-1 telescope using convolutional neural networks. With imaging atmospheric telescopes, we observe atmospheric showers of secondary particles, which are produced by primary very high energy particles or gamma ray photons. If we analyze the images, we can separate the gamma rays from hadronic cosmic ray background, reconstruct energy of the gamma ray photon and its arrival direction. In our analysis, we use modified inception architecture to analyze the images from LST-1 telescope, which is a prototype for the Cherenkov Telescope Array Observatory, and show that the reconstruction performance of this method has a potential to beat classic method of reconstruction like random forests.
Hi everyone, thank you for the opportunity to present our work. Today we will be showing a new form of machine learning architecture known as the transformer architecture to detect strong gravitational lenses. Currently, the most common method for finding strong gravitational lenses is using convolutional neural networks. From the data from the Bologna lens challenge, we were able to show that the transformer architecture can perform better than the convolutional neural networks in every category and also has better stability compared to CNNs. The results from our study are given in this poster.
Hello to everyone. In this short talk, I will present you the preliminary results that we obtained with a deep learning anomaly detection method developed to identify gamma ray paths in the data acquired by the Agile satellite. This anomaly detection method aims to detect GRPs in the multivariate time series acquired by the 5 panels of the Agile anti-coincidence system. We implemented the model with a convolutional neural network autoencoder. We trained the model with an unsupervised learning process using 5,000 background-only multivariate time series. The preliminary results obtained with the strained model prove the ability of this method to detect the GRPs in the Agile anti-coincidence data. This model can be implemented into the Agile automated real-time analysis pipeline to improve the GRPs detection capability.
Hi everybody, my name is Simone Riggi, I work at INAF in Italy, and in this short video I would like to briefly summarize our ADAS contribution. As you might know, the Square Kilometre Array will be the largest and most sensitive telescope ever built. One of the major challenges will be dealing with the huge amount of data that will be produced and extracting signs from them in a mostly automated and reproducible way. For that reason, we have started a new project called CIRASA, which aims to develop a visual analytic platform by integrating different services for visualization, archiving, and source extraction. So far for the project, we have developed a new source extraction service, which currently integrates and supports multiple source finding applications, from traditional ones to novel applications based on deep learning techniques. We are currently deploying these services on a prototype European Open Science Cloud infrastructure, so to make them available to end users. You can find more details in the poster and in forthcoming papers, and you can write to me for questions or requests for collaboration at simone.riggi@inaf.it.
Hi, I'm Gianfrance, and thanks for watching my lightning talk about a novel fast radio burst detection pipeline for Nenifar. So, in a nutshell, this pipeline is about detecting fast radio bursts in real time to trigger the storage of the time frequency signal. This avoids filling entire hard drives with the data containing little to no events. We also needed this pipeline because of the great dispersive delays faced at Nenifar, which are about 1,000 times greater than for usual radio telescopes. Apart from the pipeline itself, here are the main contributions. So we have a new approach illustrated by the animation below to the dispersion measure transform, and coming on top of existing implementations such as brute force DMT or fast DMT. We also use GPU Direct for data acquisition and a new image processing approach to pulse detection that we find promising. So if you have any question, feel free to join my gather.town.
Hello, I am Federico Cardona. I would like to invite you to take a look at my poster, which is number X2002, in which we present some preliminary test results for the correct sizing of the hardware that we lost the database for the monitoring system of the Cherenkov Telescope Array, CTA. The MON is the subsystem of the array control and data acquisition system that is responsible for monitoring and logging the overall CTA array. It acquires and stores monitoring points and logging information from the array elements at each of the CTA sites. MON is designed and built in order to deal with big data time series and exploit some of the currently most advanced technologies in the fields of database and Internet of Things. In this poster, we present the test campaign that we performed to dimension the bare metal hardware requirement, and we discuss the best set of parameters that maximize the database data writing.
Hello everyone, this is Javier Spinozza, software engineer working at Array Assistant for ESA, and I would like to invite you to see our poster about the design and development of modern science archives at the ISAC Science Data Center. The key objectives of ISAC are the long-term preservation of the data coming from a wide variety of missions and the provision of access to scientists all around the world using as many entry points as possible. For this reason, our archives have been evolving since old Java web style applications to our latest developments in Angular, and a common methodology has been defined to ensure good practices. For example, reusability across missions, maintainability, and testing. We will also show you the benefits of choosing Angular through some examples of the amazing new features we have already implemented in our science archives, such as our data and image viewers for different sources, our ESA Sky fully integrated in Angular, and of course, improvements in user experience. Come and visit us.
Hello everyone, and thank you for viewing my presentation. My name is Anthony Hang. I am a software developer for the Australian Astronomical Optics, working with the European Southern Observatory to introduce the PyCPL project. So, the goal of this project is to provide access to ESA's common pipeline library for within the Python environment. Originally, CPL was used for the construction of standardized data reduction pipelines in C. However, as Python is becoming more used for data processing over C and C++, there came a need to build a Pythonic object-oriented interface to CPL. This enables existing CPL developers to rapidly prototype new pipelines, and allows Python developers within the astronomical community to utilize the CPL toolset. So, our poster will go over the general structure of the bindings from CPL to the Python environment, using a combination of C++ and Python 11. We also detail some of the challenges we faced through the process of connecting the various layers together. Our project is currently in beta with most CPL structures and functions already bound, as well as support for executing existing CPL pipelines and building new Python pipelines. Plans have been made to begin using PyCPL to prototype new pipelines for Mavis. So, thank you for listening. If you'd like to know more about this project, feel free to visit our poster and discuss with us on Discord.
Hello, I am Eva Sciacca from the Italian National Institute for Astrophysics, and I am pleased to introduce our work related to the onboarding of space services to the European Open Science Cloud. The NIENIS project is implementing novel thematic services addressing emerging challenges in underwater, atmospheric, and space sciences to be delivered to the European Open Science Cloud, EOSC. We report on the current development status of services for the astrophysics and the planetary communities, focusing on visualizing and data management, SpaceVis, map making and mosaicing, SpaceMOS, and structure detection with machine learning, SpaceML. We present the challenges in maturing the technological solutions to TRL8 in order to obtain robust delivered cloud services within the emerging EOSC. Thank you for listening, and we look forward for your feedback on the latest release of the NIENIS space services.
The NASA Astronomical Virtual Observatory have been developing tutorials and giving workshops to show astronomers how to find and retrieve the data they need in Python, and without having to know which archive has it and how to use that archive's custom interface. This will be increasingly important as multi-wavelength and multi-messenger astronomy expands, and as programmatic data access for computationally expensive analysis becomes more necessary. The virtual observatory is used in many invisible ways across many archives around the world, and underlies, for example, many functions of the popular AstroQuery package. But another AstroPy-affiliated package called PyVO is a way to find and access these data without needing to know which archive's website and which AstroQuery module you need. In this poster, we present an overview of what these workshops do and why, and give links to the online materials that we hope will be more broadly useful to the community.
Hello, my name is Stéphane Erard. I'm an observer at the Observatory of Paris, and I'm in charge of the VESPA activity in the EuroPlanet program. VESPA is about providing access to solar system data and planetary science data in general, using a system which relies on virtual observatory standards. In the poster we present at this conference, we are using this VESPA infrastructure to provide access to a selection of data catalogs distributed in the Vizier system. So Vizier is a set of astronomical catalogs related to publications, from which we extracted only the ones related to the solar system, and this service is responsive to the EPNTAP access protocol, which is currently a proposed recommendation at IVOA. Thanks for attention.